This lesson is about the definite integral and the fundamental theorem of calculus. A lot of the beginning part of this lesson is just kind of setting it up and showing you why things work. Later on in the lesson, when you get the examples, we'll show you how it works and what you'd actually use in a problem. So here we go. So when we were before spring break, we were talking about how to find the area under the curve. And we approximated it using Riemann sums. Okay, if you remember, we broke up the whole interval, so this function right here, from 0 to 1. We broke it up into different size rectangles. Here I have 4. And you can either use a left sum, which means take the height of the left endpoint and draw a rectangle over that whole subinterval at that height for each subinterval, or you could use the right endpoint, or you could use a midpoint. All right, and sometimes we still have to do that. There are some functions that we just can't do the shortcut to, as I'll show you today. So it's still important. But we're going to learn how that goes into the definite integral and the fundamental theorem of calculus. All right, so here's just an example of several different attempts using Riemann sums. Here we have 4 subintervals. Down here you can tell, or you can see, this would be the summation notation. The big sigma is a Greek letter. In math it stands for sum, and you can see here at the bottom, possibly it's a little small. I equals 1 all the way up to n. The top number is the n, which is 4. And then here we have our parts of our function. Right here would be the actual function, 1 minus x squared. All right, and so this part right here that I'm going to highlight is the x for the left endpoint. Okay, starting at 0, and then going 1 minus 1, or 2 minus 1, or 3 minus 1, or 4 minus 1. This sets up our pattern of starting at 0, and then the next one, the first endpoint, right endpoint, the second right endpoint, the third right endpoint, because we're doing left endpoints. All right, and so it has that times the n, or excuse me, the delta x. Okay, so this basically just sets it up so it's starting at 0, and then at 1/4, 1/2, and 3/4 when you plug in 1 through 4. And then out here, we have our delta x. Okay, which is exactly what we did before spring break, as we said, hey, the area of this is approximately, using a left sum, the f of 0 times our delta x, which would be 1 minus 0 divided by 4, so 1/4, plus f of 1/4. All right, if you plugged a 2 in, you get 2 minus 1, which is 1, times the 1/4. So you'd have 1/4 inside here, that's our x, times the delta x of 1/4, plus f of 1/2, that's what you get when you plug in 3 into the highlighted part, times the 1/4. And then finally, f of 3/4 times the 1/4. Okay, and this is just the sigma notation to do that. And if you did that, I did this on a calculator previously, and I got approximately 0.78125. All right, here it is with 8 subintervals. All right, so you can tell on the first one that, hey, it's way over approximation. Here it's still over approximation, but not quite as much. For 16 rectangles, there's even less over approximation. And for 32 subintervals, we're even a less of approximation. Okay, and so the idea is, what would happen if we had an infinite number of rectangles? All right, and this is how that would look in math notation. You'd have the sum of your function at some point in each subinterval times your delta x, going from 1 all the way to n, and we're taking the limit of that as n goes to infinity. And so n is your number of rectangles. All right, and so as we talked about with the derivatives back at the very beginning of the semester, it's all about the limit. Limit is pretty much what is the rigorous way we explain and build our definitions for doing the derivative and doing what we're fixing to do. Okay, it's all based on limits. All right, so that brings us to the definite integral. Okay, we've seen this integral symbol. We've done the indefinite integral. But when you have an a and a b, that's the left and right endpoints, or the limits of integration. When you have those numbers there, all right, that tells us, excuse me, let me turn off my phone. Those are left and right endpoints. And basically what this is doing is it's finding the area under the curve. Okay, because this function right here, this limit and sigma business, is the area between the curve and the x-axis. Okay? And so that is what that means when we have the integral symbol. All right, so we have the integral symbol, we have the limit notation, okay, but we sure don't want to actually do that limit business. Okay, we could spend a whole lesson on actually doing some using the limit definition, and I can introduce you to some sum formulas. You might have seen those in your Advanced Math Plus. All right, but what allows us to do that really easy is this Fundamental Theorem of Calculus. Okay, and there's actually two parts. This is one part. We'll learn the second part or the other part in another day, another lesson. All right, but what the Fundamental Theorem of Calculus says, if I want to take the integral from a to b of some function with respect to x, okay, and so that's the area under this curve, all I have to do is take the antiderivative, that's the f of x, big F of x, and then I got to plug in the top limit of integration, and I got to plug in the lower limit of integration, and I subtract those two. And remember when we did the antiderivative, we put a plus c, but notice this is any antiderivative, so we don't have to worry about the plus c. And even if we did, we really wouldn't matter because we have a plus c here and the same plus c over here for the f of a, and they would subtract out. Okay, so this is a really powerful tool. Now down here I'm going to show you I've always wondered, okay, I know the Fundamental Theorem of Calculus, but why does it work? It didn't make any sense to me. All right, but this is kind of a thing I saw that maybe would help you understand. So let's talk about the function as a velocity function. Okay, if your velocity function is 1 minus x squared, and I want to find the area under the curve here, all right, I could do a whole bunch of, oh, that's a horrible rectangle. I could do a whole bunch of rectangles, and I could find an approximation. And I could do more rectangles than I'm trying to draw right here, even though those are not horrible rectangles. And the more rectangles, I would get the area under the curve. All right? But if you think about it, the velocity is a rate with respect to time, so our x is actually time in this case. And so we're taking rate values, our f of x are rate values, and our delta x are time values. So we have rate times time. And you probably know from even before Algebra 1, this formula here, distance is equal to rate times time. So basically what we're doing, we're finding the area under the curve of a velocity function. We're finding, hey, we know the speed, we know how fast my car is going from time 0 to 1 minute. All right, and that area under the curve just tells us the distance the car traveled. Well, we've already talked about, we can find the antiderivative of velocity is actually the position, and here is one such antiderivative. I'll put a plus c here. I think I end up using a plus 1 for my graph. And if I want to know the distance that I traveled, well, hey, at time 1, or excuse me, time 0, I'm at 1. Because f of 0 is equal to 1 here. And if I find, hey, where am I? What's the position at time 1? F of 1. All I got to do is plug it into that position function. That gives me 1 minus 1/3, which is equal to 2/3. Did I do that right? 1 minus 1. Oh, we got to put the plus 1 there. So that actually gives us 4/3. 1 minus 1/3. No, 5/3. My bad. I can't do math tonight. And so if I know that I'm at position 1, I'm at mile marker 1 when I start, and I end up at mile marker 5/3, then what's that distance? What is the distance that I've traveled between those two times? All I have to do is say f of 1 minus f of 0, or 5/3 minus 1, which would give me 2/3. And so instead of finding the actual area of the curve by doing a whole bunch of rectangles, we can think about this, the function you're trying to find the antiderivative or the definite integral of as a velocity function. We find the position function. All we have to do is plug in our endpoints, and that tells you the distance it's traveled. Okay, so that's just some kind of reasoning. It's not a proof of the fundamental theorem of calculus by any means, just kind of maybe some reasoning for those of you who care. All right, now before we actually do some examples, the definite integral not only gives you area under the curve, it gives you assigned area. Okay, by sign I mean, hey, any of this area that is above the x-axis, okay, all of this area between 0 and pi, that would have a positive area. All right, and then anything that falls beneath the x-axis and above the curve, that would give you a negative area. All right, so when we do the antiderivative or the definite integral of the sine of x with respect to x from 0 to 2 pi, we take the antiderivative. The antiderivative of sine is a negative cosine. And so we write that out. Some notation that you need to make sure that you write. Just it's standard mathematical procedure, it's standard calculus procedure. You write your antiderivative, draw your vertical line, and then go ahead and rewrite those limits of integration. All right, that way you don't forget that you're doing a definite integral here. All right, so the antiderivative of sine is negative cosine, and we're going from 0 to 2 pi. So when we plug those in, we get a negative cosine of 2 pi minus a negative cosine of 0. All right, if we think about our unit circle, remember those values. The cosine of 2 pi is 1. So we have a negative 1 minus, and then we have a negative, and then the cosine of 0 is also 1. So we have negative 1 minus a negative 1, or in other words, negative 1 plus 1. And so our overall area here, our signed area, ends up being 0. Because of all of this positive area in this first one, counteracts all the negative area in the second one, and it actually goes to 0. So if you see answers or you see problems that have negative area, that just means more of the curve was below the x-axis during that time. Okay, and we'll talk in another time about what if I actually wanted to know what is this area plus this area. Okay, that'll be another lesson. All right, so let's just look at some examples. We want to compute this definite integral. All right, step 1, take your antiderivative. So that's going to give me 1/3 x to the third. We use that power rule there. Add 1 and then divide by that new exponent. Minus This will just end up being x squared, because the 1 goes up to a 2, you divide by 2, so that coefficient of 2 goes away. And then we're going to draw a vertical line and go from 0 to 2. All right, then we plug those in. This fundamental theorem of calculus says plug in the top one. So we have 1/3 times 2 raised to the 3rd power minus 2 squared minus 1/3 times 0 to the 3rd power minus 0 squared. All right, then we do our work. 2 to the 3rd power is 8, so it gives me 8/3 minus 4 minus, and that turns into a whole bunch of 0. And that'll happen on a lot of problems. If you have any kind of polynomial, if 0 is one of your limits of integration, it's going to go to 0. You do have to be careful when you're doing trig functions or natural log or exponential. But any kind of polynomial, if you have 0 as one of your limits of integration, it's going to be 0. But double check to make sure. So now we just finish it up. 8/3 minus 4/3. So 8/3 minus 4 becomes 12/3. And so 8/3 minus 12/3 gives us a negative 4/3. All right, so it turns out that if not all, most of this graph between 0 and 2 falls beneath the x-axis. All right, a little bit more complex antiderivative here. This is x to the 1/2, so it goes up to the 3/2. Then you can either divide by 3/2 or flip it over and multiply by 2/3. All right, x squared on the bottom is x to the negative 2, so it would go up to -1 and then divide by -1, so this becomes plus 1/x. And now I need to go from 1 to 4. In the fundamental theorem of calculus, I plug those numbers in. So I've got 2/3 times 4 to the 3/2 power plus 1/4 minus 2/3 times 1 to the 3/2 power plus 1/1. All right, and then at this point, it's just doing some arithmetic. Okay, and a free response problem, you could definitely definitely stop there. Okay, anything that I could stick into a regular scientific calculator and get an answer to, they're totally fine. But for our work and for our practice, just go ahead and work it out. So 4 to the 3/2 power. The 2 on the bottom means this is a square root, so the square root of 4 is 2. And then raised to the 3rd power. So 2 to the 3rd is 8, times the 2/3 gives us 16/3, plus the 1/4. 1's a really easy one to do, so 1 to 3/2 is 1, so it gives me a 2/3 plus 1. And then now if we put it all together, we just have to do some fractions. Our common denominator would be 12, so if I multiply by 4, 4 times 16 gives me 64/12. 1/4 will become 3/12. I'll go and distribute. That'll be minus 2/3 will become 8/12 by multiplying by 4 on top and bottom. And 1 becomes 12/12. And that actually turns into a minus when I distribute. Okay, don't forget to distribute. That'll catch a lot of you off guard. So we get 64 plus 3, which is 67. This is a minus 20, so 67 minus 20 gives me 47/12. All right, let's see what else I put in here. All right, you might see a problem written like this. It's not a definite integral. It says find the area under the curve, f of x equals sine of x on the interval from 0 to pi. And so all we have to do an integral going from 0 to pi of sine of x dx. Take the antiderivative, which is negative cosine of x, going from 0 to pi. And then we plug those in. We get a negative cosine of pi minus a negative cosine of 0. Remembering our trig values, the cosine of pi is a negative 1. This turns into a plus, and the cosine of 0 is regular 1. And so it ends up that that is going to be 2. Our sine function from 0 to pi, that area turns out to be 2. All right, and on these, if I know what this function looks like, if I don't have a calculator, but I know what that function looks like, I like to draw it out, at least in my head, to see, hey, does my answer make sense? Ooh, an exponential one. Let's see if we remember how to do these. All right. Antiderivative, we know e to the negative 2x is going to be there. All right, and we figure out, hey, how do I counteract the negative 2x that would come, or the negative 2 that would come down as when I do the derivative? So we're going to have a negative 1/2 out here in front. Okay, you could even do a u substitution by letting u be equal to negative 2x and all that business. Okay, but I'm not going to do that on this one. All right, then we go from 0 to 4, and I plug it in. Okay, any coefficients that come in front, especially if it's just this one term, you can either put the negative 1/2 into both terms when you do the f of b minus the f of a, or I like just to go ahead and put it up front, okay, because it's going to be in both places. So negative 1/2, and then e to the, that'll become negative 8, negative 2 times 4, minus e to the 0 power. All right, so this becomes negative 1/2 times 1 over e to the 8th minus, this is 1, the 0 is 1. And so your answer can either be a negative 1 over 2 e to the 8th plus 1/2, or if you want to find a common denominator, you go ahead and multiply by e to the 8th on top and bottom here, end up getting e to the 8th minus 1 all over 2 e to the 8th. So a multiple choice question might have that on there. But either of those answers are acceptable. All right, and then to finish this out for this lesson, let's see at one that's going to give us an antiderivative of natural log. All right, so antiderivative 2 over x. If it was just 1 over x is the natural log, but it has a 2, so the 2 is our coefficient. And then the natural log, remember we have to do the absolute value of x. All right, and this is one of the reasons here, because when I have my limits of integration from negative 3 to negative 1, normal natural log cannot handle negatives, but if I have the absolute value, it's fine. It works totally fine. So we end up having 2 times the natural log of the absolute value of negative 1 minus 2 times the natural log of the absolute value of negative 3. And again, I could have put the 2 out in front and then put a bracket and put the natural log of negative 1 minus the natural log of negative 3. All right, natural log of positive 1 minus 2 times the natural log of 3. And so this answer can be written in one of many ways. The natural log of 1 is 0, because the base of natural log is e. So e to what power gives you 1? That'd be 0. And so you can write this as negative 2 times the natural log of 3. You could also write this as 2 times the natural log of 1/3. All right, because if you brought that negative 1 up, that would be 2 times the natural log of 3 to the negative first power. Or you could even bring the 2 inside and have the natural log of 1/9, because that would turn this negative 1 power to negative 2 power, which 3 squared would be 9, and bring it to the bottom. Okay, but any of these three answers would be fine. All right, hopefully that makes sense. I'm going to post a worksheet online on Canvas and possibly a Delta Math for you to do. And please try those out. I'm looking at possibly having a conference call meeting, a Zoom type meeting on Wednesday. I'll send you an email or a remind about that. And the time, if you have any questions, feel free to join. Hopefully all this makes sense, and hopefully you're all staying safe and practicing social distancing so we can all get back to our normal lives soon.